Hey there, physicists. So today we're going to talk just a little bit about another concept that has to do with light. The last couple of weeks, we've talked about electromagnetic waves and what they look like and the colors that make up white light. Today, we're going to talk about how to take white light and break it up into those colors. So the concept we're talking about is dispersion. But before we get too far ahead of ourselves, let's back up to what we saw when we were still together before spring break. We went out into the hallway into the commons. I don't know if you remember this, and we stretched a really long slinky all the way down, and then we had somebody at the other end that was holding that slinky. I don't know if you remember this, and we sent a wave down that slinky. And as that wave moved, I'm just going to kind of draw a nice little transverse wave here. That wave traveled down the slinky, and then when it hit the hand, well, the hand is a medium change, right? Not a big change or a small change. That's not what I'm talking about. But the the wave was traveling in the spring or the slinky, and it hit the barrier between the slinky and the hand. That was a difference in medium, a difference in the material that the wave was traveling through. And I don't know if you remember, but some of the wave traveled back into the spring. It happened to switch directions, and it also happened to decrease in amplitude. That decrease in amplitude implied or indicated to us that some of the wave was reflected because we saw the wave coming back, but not all the energy was coming back, which meant, and this is the piece that we really care about today, that some of that wave actually was transmitted into the new medium. Now, next week, we're actually going to talk very specifically about the transmitted wave of light and the reflected wave of light. But today, I just want to kind of do a little bit of an overview and talk about, like I said, one of the kind of cool concepts that happens. Okay, so the transmitted wave, this happens with the mechanical wave, like we saw with the slinky. It happens with sound. That's why even if there's a wall between you and your sibling and they're listening to super loud music, you can hear it. Okay. It also happens with light, and that's what we're gonna worry about today. So a couple pieces about light that we care about. We know that light travels at a very specific speed. We measured that speed a couple of weeks ago, and we said that that speed, the velocity of light, sometimes we mark that as c, is, I'm not sure if you remember the number, but I'll just write it down for you, 3 times 10 to the 8 meters per second. Now there's a key here, there's a really important piece, and that is only in a vacuum. So light travels really fast, 3 times 10 to the 8th meters per second. So that's 3 with 1, 2, 3, 4, 5, 6, 7, 8 zeros behind it in a vacuum. Okay, it travels really fast in a vacuum. I don't know if you remember the details about sound, but we decided that sound actually travels faster through more dense mediums. We talked about sound traveling through air versus traveling through a liquid versus a solid. Light is different. And again, we'll talk a little bit more about this next week, but I just want to let you know that the speed of light in a medium is actually slower. It's less than the speed of light in a vacuum. It's kind of cool. Okay, so instead of it getting faster and faster and faster, because those molecules are closer, it actually slows down because there's stuff it has to move through. So remember, light doesn't need a medium. Okay, so here's the other piece of it, is that unlike sound that just travels through and has a specific speed in every medium, light doesn't quite work the same way because, and this is interesting, okay, the speed of light in a medium depends on the frequency of the light. And that's what's going to lead to this thing called dispersion. Okay. Different wavelengths of light, different frequencies of light travel different speeds. And if it travels at different speeds, it's going to split up, right? If you are running a race with a bunch of other people and they all travel the same speed, then oh my gosh, you're going to go at the same speed and you're all going to stay with each other. If you hit a medium that's for some reason causes you all to change speeds, then you're all going to kind of split up, right? So there's going to be somebody that's a little faster, somebody that's a little slower, and that will split you up into different, well, frequencies or colors of light in this case, okay? So that's just, I don't know, that's kind of cool. We're going to talk about what happens when we hit there. Um, and just to be very specific to start, let's just talk about what happens when light hits that boundary. So if the boundary is perpendicular to the way that the light travels, even if they all slow down and speed up, they're still going to be moving in the same direction, all those different colors, right? And so there is not really super interesting. The super interesting thing happens when we cause those colors or that light to hit a boundary that is not perpendicular to the light itself. So I'm going to draw this as yellow. It's not actually yellow light, it's white light, but it's just, I don't have a white pen that would really work. Okay. So the funny thing that happens, and again, we're going to do some math with this next week, is that the amount that the light bends causes or is dependent on the color, okay? And actually I have a nice little graphic of this. So I'm gonna go ahead and pull it up here so you can see it, okay? So let's just look at blue light to start. I don't want you to get freaked out by all the colors. I don't want you to get freaked out by all of the what's going on. I just want to kind of trace this out for you. So white light comes in and it hits this medium boundary, right? So what does that mean? It means that out here we've got glass or we've got air. And in here, this is just a piece of glass, this triangle of glass. Okay. Glass is more dense than air, and so it's going to cause that light to bend. So that light, this white light that's coming in, some of it is going to bend like this. Okay. And that's kind of cool. I'm going to go over to the next picture and then we'll back up a second again. If we look at this light, same light that's coming in, I'm yellow actually, so we don't get ourselves confused. So that's my white light coming in. The red light has a different frequency, right? I don't know if you remember this, but the red light, the frequency of red light is um, less than the frequency of blue light, okay? Because the energy of the blue light is bigger, right? We've got higher frequency, more energy. It's going to bend less as well. So that red light actually bends less when it hits that boundary. And then because of the way this triangle is formed, that red light is going to bend again, and that blue light is going to bend again. And I don't know if you see the subtlety of this, but the really nice thing about this triangle of glass, which you may also have heard of as a prism, okay, is that the the light bends such that it separates that light. So the light that came in as white light, okay, bends and separates all of those colors out, because remember red is at one end of the visible spectrum, the visible part of the spectrum, excuse me, and blue is at the other end. I guess you have violet at the very end, but it's you get the point, okay? That's going to spread all of those colors out, okay? And that's how we get the beautiful rainbow from a prism, right? That's how we get the Pink Floyd cover. That's how we get all of those funny rainbows that show up. I don't know if you have any like cut glass anywhere in your house, like a um, crystals, or like I know on our front door we've got some little pieces of cut glass, and so in the afternoon we see rainbows everywhere in our house because that white light that comes in from the light in the west, right? It splits up into all of those colors, and so we have these little rainbows that form all over our house. So just something, and this is just kind of leading us into the rest of the lesson for today. So if you have a window, just a plain old window, that's funny because, right, it's a plane. Um, the white light comes in, so we'll have the white light come in like this. And it's kind of interesting because if you were inside the window, you would actually see those rays of light bend and break out into their pieces like so. But then because of the geometry, it actually happens that the red light's going to bend back and the blue light's going to bend back so that it's actually in the same ray. And so you just get this white light back. So you don't get a rainbow from every single piece of glass that light travels through. It's because this thing is a prism, because it's got this nice cut on both sides so that you don't have it parallel, that you get this nice dispersion of the light. The rest of the lesson that you're going to work through, there are a couple more videos for you to take a look at and some things to think about, have to do with having a circular change in medium, okay? Not made of glass, that would be super dangerous, but in the air, we have a lot of these little water spheres, also known as raindrops, okay? And when they are suspended in the air, you can get a beautiful thing called a rainbow. So anyway, go ahead and take a look at the next couple of videos and learn a little bit about rainbows. It's really cool, and there's some good physics in there, friends. Thanks so much, and we'll talk to you again soon.